Hi everyone and welcome back to our series Build a Large Language Model from Scratch. In previous video, we discussed about the self-attention mechanisms and we also implement it using Python and PyTorch. Now in this video, we discuss about the causal attention mechanisms. For many of the large language model, you will want the self-attention mechanisms to consider only the tokens that appear the period to the current positions, high and predicting the next word in a sequence. Now in this one, we discuss about the causal attention, right? So causal attention is also called the max attention. Is an specialized form of self-attentions. It restricts here a model to consider only the previous and the current inputs in a sequence. See what I'm actually talking about. Let's say I have one sentence called, let's say your journey. Let's say your journey start with one step. So if I apply here the self-attention mechanism, it will considering his both what from this side, I mean from left and right side. But when you apply here the causal attention mechanism, I mean the max attention, it will just considering this word. Let's say I'm going to consider his this word, my the current position of the sentence, I mean current position of the word, and it will considering here this previous word which is coming. And then after this of this word, it will making them as zeros. It will not going to consider them. It's called the marks. So why you actually basically need to using here this kind of attentions, the causal attentions, so that our model is not going to do the overfitting problems. Okay, because in the case of the machine learning, so you have some seen data, you also have some unseen data, same like that. Okay, now we'll modify the standard self attention mechanism to creating here an causal attention mechanisms, so which is essential for developing the large language model in a subsequent chapter to achieve the GPT like large language model. So for each token process, we will max out the future token. See, we will max out this with one step. We're going to maxing this out. So you can also go in the book that you can see, the build the large language model from scratch by Sebastian Rashka. So hiding feature what with the causal attentions. So causal attentions, also known as max attention, is a specialized form of self attentions. It's restricted model to consider previous and current input in a sequence, high-end processing and any given tokens. So if I see this kind of examples, you can see we have our word, I mean we have a sentence called your journey starts with one step. So when you calculate here the attention weight for the input token corresponding to the step and your, okay, you can see we have this kind of matrices. But if you see these matrices, you can see maxed out the future token for your token. So if I consider the word called your, and for this your word, it will just considering here this first block. It will making this four rest of the five blocks in a empty. Okay, same thing for journey because the second one, so it will corresponding to this x and y axis. These two value is filled, and 3 value is filled, 4 value is filled, 5 value is filled, and in the case of step, we have the full number of data with the in the size of context length. Okay, so how can we basically apply here the cause attention marks? So first you see that we calculate here the attention score. It is the unnormalized data, and then we apply here the softmax so that we can also get some kind of normalization data, which is sum up of the ones. And you can see then we got in here the attention weight, and we already discussed everything in our previous video. And after that, when you apply here the causal attention marks, to marks with zeros above the diagonals. See, above the diagonals. So if I go on that, if I go on this box, sorry, not here. So you can see this marks is actually applied in the diagonal part. In the diagonal part. If you don't know what is the diagonal, then you can just learn about the matrices. So diagonal means, let's say we have one number called 1, and we have, let's say, another 1, and let's say 1, let's say 1, let's say 1, and like that. Okay, I just assume here the four things. So it's one kind of Pascal triangles. So this is 0, 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 and this is 0. And you can see above the diagonal, this line, this all of the value is considered as a max, and all of the value is nothing but the zeros. Okay, I mean max about, you can say maxed about diagonal. That's it. Okay, so now you can see in the same thing here. And after that, we are going to normalize them. We are going to normalize the rows, and we got in here max attention weight. So you know that how can you calculate the attention score and how can you get the attention weight? Now, when you do the diagonal of that, you'll get here one normalized max attention score, And when you apply here the softmax activation function, then you can get here max attention weight. Okay, so that you can see. Now what I can do is simply going to implementing this out. Okay, so let's go on the code that's our code that you can actually see on here. So now what I can do is simply going to creating here our queries, keys, and the attention score. So how can you do that? Let's try to compute this out. So we have our as a b2. So as a b2, I mean our self attention mechanism that you can see. So from the self attention mechanism, you're going to calculate here the causal attention mechanisms. So self attention mechanisms, the version number 2, then you're going to taking here this w query that you already implemented. So we can say the w, we can say the query, and then we're going to passing here our inputs. Okay, you can also see the inputs how it look like actually. So I recommend you, if you missed the previous video, please check out. So you can see here, this is nothing but my inputs. Okay. So we're going to passing here the inputs, and this is nothing but our queries itself. So let's say queries, and then we're going to also taking here our keys. Let's say self. Okay, not self actually. As a b2, as a b2 dot w, and you can say that the key, and then you're going to passing here our input itself. Okay, and this is nothing but our queries. So let's say keys. Okay, keys. So you can also printing this out. Let's try to printing this out first. Let's try to printing here our queries, and let's printing here our keys itself. So you can see here, this is our the queries, and this is our keys itself. Okay, and you can see in the case of keys, the value is also different, and you know that how can you actually compute them. In previous tutorial you already do that. You can see this is our diagram that you can see queries, the keys, and the values. Okay, and if you see that, how can you implement it? We have one input tokens, and you actually multiply with the metric, multiply with the wq, wk, and wb, and then we got here this queries, keys, and the values. Okay, that you can see. Now, what I can do is simply going to do the matrix multiplication of the transpose. If you see that in these cases, we basically do the transpose. Why? Because our matrix size is not same. So if I multiply these two matrices, this dimension is 6 cross 2, and this dimension is 6 cross 2. If I multiply it, we unable to multiply it. So you need to transpose this keys matrix so that we can multiply like that. So let's say we have a matrix called 6 cross 2. Let's say 6 cross 2. And if I multiply with the 6 cross 2, our second matrix should be transported so that our matrix is look like that. Then we can simply going to multiply it, and we got in here a matrix size of 6 cross 6. Okay, okay. And same thing, you need to also do it in order to calculate here the attention score that we do. So then this our attention scores for all of the matrices, I mean all of the words. So you can say that queries, and we can simply going to taking here the transpose of the keys itself. So keys dot transpose. Now we got our attention score. Now we have to calculate here the attention weights itself. So let's say weights, and then we can apply here the torch dot softmax. So let's say softmax, and then you can simply going to give it to here the attention score that you have, and as well as you can dividing here with the root over decay. So that's why the self attention mechanism is called as a self dot attention mechanisms. So we're going to take it from keys dot shape, and then you're taking here the -1 so that you can getting here all of the shapes, and then you're simply going to escalate it 0.5, I mean root over. Okay, then we're simply going to making here the dimension, let's say give it to here -1. Okay, so that it is taking here all of the columns. Now you can printing here the attention weight. Let's say print here the attention weight itself. So that's our attention weights. So you can see that's our attention weight for each of the word. So our word is nothing but a your journey start with one step that you can see we discussing on here maybe. So here you go. Kidhar chala gaya? Your journey. Okay, should be your. Okay, your journey starts with one step that you can see. Okay. Now, what we can basically do? We can implementing here the second step using the PyTorch trill functions. Why trill? If you go on the documentation of the PyTorch, so let's say PyTorch trill and try you. So you can see how it actually work. PyTorch try you and PyTorch trill. So it also, you can see some kind of informations from the Google Gemini. So if I go on here, so you can see here it will taking here one tensor, input tensor, and then it also give it here the diagonals. So what these actually try you actually do, it will try to making here all of the upper point uh, should be the zeros. I mean upper value you can actually add it, and this tree is actually doing here the lower value should be the zero. That you can see 0 0 0 0 0 0 0 0 0 like that. Okay. So now we can simply going to using here the trill so that you can also implementing this kind of thing that you can see. I mean, you're going to creating the marks itself. So we can simply going to applying this out. So that's what I can do. We're simply going to first taking here the context line, how many context we have. So for the sake of the simplicity, we just considering here the 6 cross 6. I mean, we have the 6 input tokens. So we take it from the inputs itself. So we can say that context length. So we implement it based on the attention score because you're going to apply here this causal attentions in our attention score itself. So we can basically take it from the attention scores dot shape. So let's say attention scores dot shape and taking here the zero because the shape is nothing but the same, and we can take in the first index. That's our context line. Now we're going to creating here a max simple. I mean simple max. We're going to creating that using this torch dot trail function. So let's say torch dot trail, and then it's simply going to using here torch dot ones. I mean, you're creating here all of the vectors of the ones to the context vector. Let's say context length and the context length. Okay, then we simply going to print this out. We're going to printing here the marks simple. One more thing that is someone said that I maybe copied someone because actually I am following here this book that you know that this book, the build the large language model from scratch by Sebastian Rashka. So I just do here everything from this book that you can see. Everything inside the book. I just explain each and every lines so that you guys actually understand it easily. That's my motive to do that. And all of the code you can also get it in our in this book as well. So I just copied all the code from here, but I also implementing some of the information on here. I mean, just do some changes based on that because when you try to implementing this out, you may face some kind of error. I also try to make it simplify as well. Okay. So what I can do now, we're simply going to implementing it from scratch. Okay, I just follow this book. Okay. Also, I have my as well as my notebook that I already read it from this book, and I'll give you this kind of tutorials. Okay, that's from my sites. So now you can see we have one matrix which on all the values nothing but the one, the lower ones and upper one is nothing but the zeros. Okay. Now you can also implementing here this try you. So you can see here now all of the diagonal, I mean the above down, it's nothing but the zeros. And above the value is nothing but one. So try you means the above value, which one is one, and real is nothing but the lower value, which one is nothing but the one. This is how the star steal function actually work. Okay. So you can see that how can you basically implement this out. Now what I can do, we simply going to multiply this marks with the attention weight to zero out the values above the diagonal. Why? See, if I taking this full data, I mean taking this full matrix, if I multiply with 1, we have the same value. If I multiply with 1, we have the same value. If I multiply with 1, we also get here the same values. But you can see some different types of values you can get. You'll do it later, we explain later. But for the simplicity, if I multiply with the 1, we got the same value which is available in this matrix. And rest of the value is converted into 0 because we multiply them with the zeros. Okay, this is how just getting the marks. We are not going to do the normalization yet. We just apply here the unnormalized data. You can see marks with 0 above diagonals. We implementing these things. This is the unnormalized. And after that, you can normalize this later on. That you can see this is normalized things. You can see 1 because we know that the whole matrix sum up should be the 1. This is called the normalized, right? So we can simply going to do this out. Do this out. We can simply going to closing this out. It's not needed at all. Now we are going to multiply with the attention weight that we calculated with this max simple, so that you can getting here some kind of max matrix. So what I can do, we can simply going to say that let's say attention weights. So let's say attention weights, and you can multiply it. Let's say multiply with the marks simple. Let's say, oh, marks simple. Okay, so this is our marks simple. Now you can simply go into print this out that you can see. But here is also one problem as well. So you can see we successfully creating here this marks. We successfully creating here this marks. But here is also one problem. See, if I join all of the value from the first matrix, we don't get the value sum of the zero because it is an unnormalized data that you can see. It's an unnormalized data. Now we need to normalize zero. So how we can basically normalize zero? We basically taking all of the values and divide them with the sum of them. Okay. So let's say implementing this out as well. So let's say this is our masked simple dot sum, and you're making her dimension as a -1, and then keep dimension as a true. Keep dim as a true. That's it. So this is the row sum. We're just taking the row of the sum, and after that we are going to divide them. Okay, so let's divide them with the boxed simple divide by with the row sum. Okay, it should be the plural number because it had the multiple number of values. So you can say that row sums. Maybe you may get some kind of voice issue. It's better you can use the headphones because my microphone that I'm actually using, it's 4 years ago I buy. So I had to also buy another one. So then maybe voice is coming great, but I hope so. You will able to hear me as well. It's better you can use here the headphones. Okay, for the great audio. Okay, so this is by Mark simple norm. So what I can do is simply going to printing this out. Let's start to printing it out. Printing here marked simple norm. Now you can see we got the matrix which one is exactly same as like that you can see. It is exactly same as like that you can see on here. Okay. But here is also one problem. Here is also one problem. See, why this problem? So you just divide them with the number of rows itself. So when you have the large number of length, when you have the large number of data, so how can you divide them? It take more amount of multiplication, right? It take more amount of summations. So what you can do, we basically using here the softmax activation functions for the normalizations. But if I apply here the zeroth to the softmax activation functions, the value is changed. The value is changed. So if I going to show you here, let's taking here one tensor. Let's say torch dot tensor, and you're taking here some other tensor. Let's say 0.0. Let's say 2.0. Let's say 3.0. Okay, that's it. And then if I'm going to apply the torch dot softmax, let's say torch dot softmax, and if I apply the x and dimension is equal to let's say 0, and then we simply going to result, and you can simply going to printing this out. Let's say to print result. So you can see here how you actually using here the softmax on the zeros, we got here a value called 0.0351. That means our value is changed. Our value is changed. But in here we need here the masked. We need here the masked. But when you apply the softmax in this value, we got in here this kind of thing. The value is also same change. Now, if I apply it on real-time data, then you can see what actually happening here. Let's say torch dot try you. Okay, torch dot try you, and you can apply here the torch dot ones, and then you're simply going to passing here the context length. Let's say context length, and the context length, and as well as I'm going to using here diagonal is equal to -1. Okay, so 1, sorry. And then you're simply going to take it as a max itself. Let's say max. And then if I apply here the softmax to these zeros, we may getting here 0.351. So now if I'm going to make it torch.infinity. What actually happened? It's a torch.inf. Okay, we got some error. Module torch has no attribute called inf. It's nothing but called the infinity. Sorry for that actually, because I am using here a lower version of PyTorch. So that's why this infinity is not actually supportable in my cases. So I can using here the NP. Okay. Now how I am using here this minus NP dot infinity, you can see here we got the value 0.00. It not changes. It not changes. It will try to making this normalized. It will try to making this normalized. So same thing you can also apply here in our code as well, so that you can also getting here this kind of minus infinity. We can getting here the minus infinity. How you apply it, you got here 000 like that, right? We can apply here. We can getting here 000. So this is the main catch. This is the main catch. Because when you just apply here the softmax in our zero, we may got in here some kind of random value. It will distribute them. It will distribute them. Okay. So that's why we're using here this INF. See, if I am going to open my terminal and let's say import. Okay, and I don't need to import the terminal actually. I can also printing this out. So if I'm going to printing here my PyTorch version, so let's say torch dot underscore version. So you can see here I am using here 1.7.0 and Coda 10.1, which is lower version I am actually using. But if you're using here the updated version, your torch.inf is also supported. Okay, I just use it for the simplicity. But how in the latter in the next few tutorial, if it is supportable in my own laptop, so I can using here the Google Colab because I don't have it, and also installing PyTorch is quite the big issue. In some kind of cases, it's not it's installed very well. Okay, so torch trio. So how you actually apply the trio? So trio, all of this value which is above, which is less, it will making here other zeros, and above them it will making here one, because he actually using here the ones. So if I using here the tree, it will making here the lower value should be the ones, and upper value is a zero. Upper value is a zero. So how you apply here the true, so it will making here this up above as a one, so that you can convert it, and less of them are the zeros, like that. Okay. So we can simply going to apply it to the attention score. So let's say attention score. Now you can simply going to using here functions called maxed fill, so that it will fill it based on the max value. So now you can taking here the boolean, and then you can apply here this np.inf. So the both they actually give here torch.inf. So I'm just going to give it here minus np.inf, and this is nothing but our marks itself. Now you can printing this out. Okay, you can printing here this maxed. Okay, anything wrong? Tensor object has no attribute called maxed fill. Okay, sorry, my bad. Oh, it's got. Okay, now you can see this is nothing but the minus infinity, minus infinity, minus infinity. But here is also one problem. See, it's nothing but 0.2899. It's not normalized, because if I sum up this one, we don't get any value which is sum up to the ones. So when you get the sum up to the one, it's nothing but the normalized, right? Now you can simply going to apply here softmax activation functions. And how you apply here softmax activation functions in this minus infinity, we got here the value as zeros. We got the value as a zeros. Now let's start implementing this out. It's a torch dot softmax, and then we can simply going to say that maxed, and let's say keys dot shape, and let's say -1, and then you can say that 0.5, and dimension is 1, and here you can do, you can simply go into creating here a variable called attention weights. So this is our attention weights itself. Now you can also print this out. Let's set up printing here the attention weight. Now you can see here attention weight same as it is that you can see in the book. Same in the book. Okay, same thing. Now we can also modify the attention weight to compare here the context vector by, we can say the attention weight into the values. So you can also creating here the context vector. You can just going to using his values. So this is give it here one kind of context vector. Okay. So you can see you got in here one kind of context vector, but here is also one catch. So you need to also maxing here the additional weight with the dropouts. So if you have the knowledge of the neural network, you know that what is a dropout actually. So थोड़ा पानी पी लेता हूँ, इसके बाद मैं आता हूँ इसको डिस्कस करने के लिए. So now let's discuss about the dropout. So what is exactly the dropout? You can just go on the Google and search for that. So let's say drop out in NM. So you can opening this out. So dropout in neural network operates by randomly selecting here a fraction of neuron to be set to zero during the each training sessions. So if you know about the neural network architectures, so if I am drawing this out, just one simple neural network architectures. So in the case of neural network, we have the input layer. So you have the input layer. Let's say this is our input, and also you have one hidden layer, as well as we have one output layer. Okay, so it's connected here. It's a fully connected layer. So like that, and you can also connecting it like that as well. And same thing here, and same thing here. And then you can say that here you go, here you go, here you go, here you go. Okay, not like that actually. To give it a line hand here. So you can also give it here. So this is nothing but our input layer. Okay, this is our input layer. It's our input. So this is our hidden layer. So this is our hidden layer. You can say that hidden, and that's our output layer. So what exactly the dropout do? So dropout actually helps to reduce the overfitting problem. To reduce the overfitting problem. Now, what is the overfit? Let's say we have one data. We just train it using here any machine learning algorithms or using here any neural networks. So let's say our model is working well in our training data, I mean our seen data, but it unable to predict in our test data, I mean our unseen data. So it's called the overfitting. It's when it will just learning this training data well, but unable to predicting here the test data. Okay, this is called the overfitting problems. So the dropout reducing here this kind of overfitting problems. It's generally happening in the case of the deep learning architectures. So it will important to emphasize the dropout is only used during training and disabled afterward, and is basically used in the case of the hidden layer. Okay. So I just read it from the book. So dropout is a deep learning technique where randomly selected hidden layers in it are ignored during training, effectively dropping them out. I mean, you set them as a zeros. So because it's a simple neural network, if I have the large language model, we have the vast amount of parameters. So we some of the parameters is lazy. So you can randomly select in them and you can set them zero so that our computation is quite speed and our model is not going to face the overfitting problems. So in the transformer architectures, it including models like GPT. So dropout in attention mechanisms, it's typically applied in the specific time. You can apply it after the calculating here the attention weight, or you can also apply it after the attention weights to the value vectors. You can apply it on here. Now what I can do, we simply going to implement it, and in this here for example we using here the dropout of the 50%. We using here dropout of the 50%. It's mean 50% of the neurons are deactivated. So if we're taking as the full neuron as a 1, and if I deactivate it here 0.5, then we're cutting here a value of call 2. Okay, high end we deactivate them. Okay, so for the sake of the simplicity, just take it here the 0.5, but high end actually implementing here our GPT model in the next chapters. So you're using here the lower dropout layer, let's say 0.1 or 0.2. Okay, now let's go on the code and try to implementing this out. So let's say torch.manual manual. Okay, it's a manual sheet. Let's give it to here 1 2 3, and then we can creating here a dropout. Let's say dropout.nn.dropout, and then you can give it here 0.5. I mean 50% of the neuron should be deactivated. This is our dropout layer. So we can say that this is our dropout. And then after that, what I can do, we simply go into taking here an example just for showing. So you can, let's say torch.once, and then let's say 6,6, and then I want to printing here this example. Okay, just it's taking here, and now we need to apply it to the dropout as well. So dropout the example. So you can see it will sum up to the what 2, 2, 2, 2, 2, 2, 2, and some of the 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, like that. Okay. Now why this 2? Why this 2? Oh, you already discussed about that, right? You can see we got in here a value of the 2. So high in the value is not actually deactivated. We got in here the value of the 2 that you can see, and the value is deactivated is nothing but the zeros. If I go on the book, that you can see, so in here maybe, yeah. So you can see in the case of dropout, some of the specific neurons are deactivated that you can see. So your journey start with one step. So that you can see these neurons are actually dropout marks. Dropout marks with randomly positions to be dropout. It's mean 50% of the neuron is deactivated in here. It will randomly selecting here the 2, 3, or 4. Okay. So then we are going to apply here this dropout marks to our actual value. So in here, if I see, so this is a 1, this is our starts, this is our dropout marks, this is our dropout marks, and you can see in this rows the journey is full and visible because we have the marks here, and also here. Same thing with the start that you can see here, same thing on here. Okay. So the dropout marks applied to the attention score will zero out certain attention scores. Now you can directly implementing this out, right? So what I can do, we just implementing it here that you can see in our code. Implementing this out that you can see some of the value is going to convert the 2 and some of the value is converted into the zeros. Now what I can do, we're simply going to implementing here in the dropout to our attention weight. Okay. So you can simply go into using a Trojan manual sheet. Let's say manual sheet, and let's say 1, 2, 3, and then you can apply it to the attention weight itself. So let's say printing here the dropout to the attention weights, our attention weight, because it applied. So you can see here this is a 2, this is 0.0002, and some of the bill is deactivated. You can see while we do the training part. Okay. So this will actually help us to reduce the overfitting problems. Okay. Now we're going to implementing here a compact casuals attention class so that we can also use it in our GPT architecture while we do the training part. Okay. Now let's start implementing here a compact casual attention class. If I go on the book that you can see. So implementing here a compact casual attention class. So it is nothing but a class itself. Then you want to also implement here the forward pass as well. So if I see this one, we implementing here the simplified self attentions, implementing here the self attention mechanisms. Then you also now implementing here the causal attentions. And now in the next tutorial, we see that how can you implementing here the multi-hat attentions, which is a big chapter and which is a big topic. Okay. So now let's start implementing here this class, the causal attentions. Let's go on the code. Then let's try to implementing this out. Let's take in some shell as well. But also one more thing here. So while we passing here the data in the large language model, we basically pass the data in the from a batch. In the from a batch. Okay. In the from a batch size, we passing the data to our neural network. Same thing in the LLMs because LLMs is a neural network itself. So you have to passing the data in the from a batch. Let's say I have a sentence called your journey. That's your journey starts with one step, right? Now let's say I have another sentence. Let's say my name is, let's say, knowledge doctor. Okay. So this is our first batch. So in the first batch, it will go this sentence. In the second batch, this sentence also go. That's we need to passing the data in the from a batch. Because we are not going to implementing here for the one sentence. We're going to implementing here the last corpus of the sentence. That's why we're to implementing here in the case of batch. So let's say also implementing here a stack of batch. Let's say torch dot stack, and then you can passing here the inputs. So let's see inputs and inputs because this is our sentence, the context length. So we give it here dimension of the 0, and then this is our batch. So let's say batch. And now you can simply go to shape, check the shape of the batch. So let's say printing this out, printing here the batch dot shape. So you can see our shape is nothing but 2 comma 6 comma 3. If I check the shape of the inputs, let's say inputs dot shape, you can see 6 comma 3. So 2 is nothing but our batch size. I mean 2 centers we can passing on here, and 6 cross 3 is the dimension of the inputs. Okay. So if I see this inputs, it's nothing but have the one batch because it's just having one of the batch of the centers. Your journey start with one steps. Now you have the two batch, you can simply going to passing here the another sentence as well. Now going to implementing here the causal attentions. Let's start implementing this out. Let's say class, we have the class called causal attention, and then you have the nn dot module, and then you have the def init, and then you can say the self, the d in, the d out, dimension of the input, dimension of the output, the context length, and then you can have the dropout, and you also have the qkb bias as a false. You already seen this out. What is that actually? So if you're not following here at this series, you need to, if you just go on here, the if you just watch here the first time this video, so you're unable to understand this out because you need to also see the previous video as well because we discuss everything on here. Now let's try to initialize this in our variable. So let's say the d out as a d out, and then you have the self dot w query. You can also copy this out from here. You already implemented this in our previous tutorial, so you can copying here this code. Okay, you can copy it here, this query, and the matrices. So you have the self.w query and nn.parameter. So instead of parameter, we can using here the linear layer. So you also implement this, right? Linear one. So how is it? Okay, this was, you can copy this. You have the q bias that you can see, you can be bias. So sorry about that. We can simply going to patch it on. Okay. So q query and then dot linear layer, you have the d in, the d out, and the bias is q carry. Now you can also initialize here the dropout. So that's our dropout itself. And then we need to register the buffer. Let's say register buffer with the marks so that you can also apply it. Okay. If you don't know what is the register buffer and how to implementing the causal attentions in the transformer, you can go and check out the videos in my playlist about the transformer. We also implementing here this kind of register buffers. Okay. Now in here, what you can do is simply going to copy it here, this code that you already implemented. Okay. So here you go. This is stars dot try you. This is our marks itself. Same thing. We just copy it from here. So tros dot try use, and we have the tros dot ones, the context length, and diagonal at the ones. Now let implementing here the forward functions. Let's say def forward, which is taking here the self comma and the input tokens, I mean inputs. So now we passing here the data in the from a batch. If I see that we just passing here the data for the single value, for the attention of single value, but now we need to passing here the data in the from a batch. So we can basically passing here the inputs. Now we need to also passing here, we need to actually extracting here the batch number of tokens and the d in from our shape, from our input shapes. I mean our input shapes look like that. Batch, our the input tokens and number of dimensions. Okay, so let's try to extract it out. Let's say x dot shape. So x dot shape, we have the batch. So each our batch, then you have the number of tokens, and we have the d in. Okay, dimension of the inputs. We just take it here, 6 cross 3 matrix. Higher 6 is nothing but the number of tokens. So the tokens are, and 3 is the dimensions of our d in vectors. Okay. Now we can simply going to apply it to keys. So let's say keys self dot w underscore key, and then you can simply go into passing here the x, and after that you need to also do the same thing for queries and value. Okay, so you also do it in on here as well. our functions that we created in the self-attestation mechanism that you can see. The same thing, we can copy it from here as well. We can directly copy it, but the shape is different. That's it. So in here, you can see the keys, the values, and the queries itself. Now we need to calculate the attention score. Let's say attention scores. So you can calculate the attention scores using the queries and the transpose of the keys dot t. Okay, keys dot transpose. Or you can also using here this one, keys dot transpose of 1,2, because we passing the data in the from a batch. We have the 2, 3, 6. Okay, you can using here this 1, 2. Okay, just making the keeping the dimensions of the at the first positions. Okay, that you can see batch. So why this transpose actually? Because so that you can transpose the dimension from the 1, 2 and keeping the batch dimension at the first index of the positions. Okay. Now what we can do basically, now we can simply going to calculating here the attention marks field that we already implementing this out. Marks field किधर गया भाई? Yeah, इधर पे आ गया. So let's copy this out. So this is our marks itself. Now we can simply go into apply it to the attention scores. So let's say attention scores dot marks field, and you can pass in here self dot marks dot bool, and then we're taking here the number of tokens itself, number of tokens. Okay, tokens uh, from the oh from the rest of them. So we can say that the number of tokens itself, the numbers of tokens, so that it's not going to go out. Okay, see why actually I'm talking about. So in the case of steps, you can see it has the 6 contexts. So you're just taking the token number from starting from 0 to last. Okay, so that it's not going to beyond these matrices. Okay, so that's it. Now you can give it to here np.inf, and after that you're going to calculating here the attention weights itself. Okay, let's say attention weights, and then you can using here softmax, and you can simply going to copy it. You already implementing this out, right? You can implementing this out. So you can say that torch.softmax, and you can passing here this attention score itself. So attention scores divided by key start shape of -1, and dimension is nothing but the -1. Okay, so -1 itself, we maybe do one mistake on here. We make it 1. Same thing, we got it here. So now what I can do, we're simply going to apply here the dropout. Let's say self.dropout, and you apply it to the attention weight. Let's say attention weights, and then this is our attention weight itself. Okay, this is our attention weight itself. So let's say attention weights itself, and then now we can go to convert. I mean, we're going to calculate the context vector. What's the context vectors? I guess the context vector attention weights, and we can using here the matrix multiplication of the values. Let's say return here the context vector. Let's say context vector. Cool. Now we can say that the torch.manual sheet 1 to 3, and we can have the batch size. So let's say batch shape, and we're taking the batch shape of the one so that it can gauge in the batch shape of the context length. So let's say context length, because in our batch we have the context length as well as the shape of the inputs, and the context length is nothing but the 6 itself. Now we can apply here the causal attentions. Okay, causal attentions, and then you can apply here the d in, the d out, as well as the context length, and then you can simply go into passing here 0.0. This is nothing but our q key bias, and then we have the CA, and after that we simply going to print it in the from a batch. So let's say context vector, context vects, okay, vectors CA of the batch. I mean based on the batch size. And then you can print in the context length. So let's say context backed dot shape, and we can also give it to here the shape of the context vector. Let's say shape of the context vectors. Okay, anything wrong? Okay, number of tokens is not defined. Here is it. Forward methods, the number of tokens. Okay, number of tokens is on here, right? Number of tokens. Here you go. Okay, got it. Again. Okay, float object is not callable. We have the attention weight in our dropout. So unfortunately, we actually got in here this kind of error because we are not going to initialize here the dropout layer. That's my bad actually. So we can say that nn dot dropout. Okay, this should be the capital. So drop out. Okay, and then I'm going to passing here the dropout value, which is coming from the parameters. Okay, so dropout. Now you can simply run this out, and then you can see the shape is nothing but 2 cross 6 cross 2. Okay, this is basically the batch size of that. If I see in my box, so the shape of the context vector is the same as it is as our book 2 comma 6 comma 2. Okay, so that's it for today. Now I hope you enjoy this full tutorial, and in the next tutorial we discuss about the multi-hat attentions. So this person is done, this person is done, as well as this person is also done. Then we go to the multi-hat attentions, and after that we are going to implementing here our GPT models. Okay, that you can see implementing a GPT model from scratch to generating here the text. Okay, so thank you and bye bye.